There's a right old delay on it, don't Right, okay, so I've done this as two separate little tables. What you might get in the exam, if they ask you to do something like this, then they'll do a separate table for each, but I just thought, well, there's no point in writing it all out again. Okay, so in this instance, I've put trues and falses down. Okay, what I'm going to do is I'm going to do this again with noughts and ones, just to show you that, and also show you how to write this bit. Okay. Once we've been through these, what I'm going to do is I'm going to draw a stupid circuit, meaningless circuit on the board, and just go through how you build a truth table up to describe that, and then I'll give you a couple to do. Okay, so the easy one, not, which acts just with a single input, if something is false, you get the opposite, which in binary is really nice because there's only two things. So the opposite must be true, and if we've got something that's true, that is false. So you saw that the other day when we did the file stuff, when we wanted to see if we were at the end of the stream, but we wanted if we were not at the end of the stream. So we use not. Okay, the other ones, OR and an XOR, require two inputs. Two things that we're basically comparing. Okay, when we've got OR, as long as we have got one of the inputs as true, then we will get true as an output. Okay, so we've got false on both of those there, so the output will be that. There's a true, there's a true. There's two trues, but we don't care. As long as one of them is. That's what OR is. Okay? The AND, in this case, we need both inputs to be true for us to get an output of true. Okay? So we look at the A's and B's, and one thing you mustn't do, and I did when I went through with the other class, I went and started reading columns all over the shop and made a right mess of my example. But you must make sure that you're looking at the right ones. You'll see why when we do the circuit. So I'm looking at that and that. No, there's a false on both of them. No, there's at least a false, that don't work. There's another false, but in this last instance, they're both true. So we end up with false, 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 true. Okay. Everyone happy with that? So in my head, because my head works this way, I tend to think there's those two as opposites, but they're not. But to me, it just seems like an opposite sort of thing. The exclusive OR, okay, if you do any statistics stuff, you might have come across something called mutual exclusive. Okay, when you're doing like probabilities and things like that, and combinations and a bit of stats. But all it means is that we get an output of true only when the inputs are different. Okay, which might not seem very useful, but it is an incredibly useful logic gate. So here, they're both the same, so we get false as an output. Here they're different, so we get true. Here they're different, so we get true. Here they're different, so we get false. Here they're the same, so we get false. Okay, so when we're programming, the three common functions that we'll use are the not, and, and or. Exclusive OR has got some incredibly useful properties. When we're machine code programming or assembly language programming, XOR is a quick way of setting a register value to 0. So for instance, if I was working on a Z80 machine, I might say XOR A. Okay, and that command would say, take the accumulator and apply exclusive OR to itself. And because it's the same thing, it'll set everything to 0. Okay? And it's one of the super quick operations of the CPU. So you see that in code quite a lot, where someone's doing that. I'll just mute that, because I think that's going to... Shut up, headphones. Okay, anyone got any problems with that? Right, I'm going to redraw the table, but I'm going to do it with noughts and ones this time. Just to show you that it's the same, but just to show you how to build this bit up. Like I say, it depends on the context. If you're doing truth tables, you know, like that one in the mock that we did with the food, and that was all truths and falses, wasn't it? That logic problem. So it would have made sense to use truths and falses if they'd have asked us for truth tables for that. Okay, so in general, naught would... Oh, I picked up a duck pen. Naught would... I'm going to fix it with the other pen here. Naught would represent false. I love my videos. They're so pro. 1 would represent true. So the opposite of naught is 1. The opposite of 1 is naught. When we do the inputs for these ones that revolve more than one input, what we do, if you start from the right hand side, so we've got A and B here, and I'll do an example in a minute with A, B and C. But we've got A and B, so start with the right hand one, and all you need to do is just say, right, okay, I'm just going to alternate the values. Every single row. Every time I move this way, we have a little bit longer before we alternate, in powers of 2. So this time the A, we're just going to go 0, 0, 1, 1. So every 2. If we have another column, it'll be every 4. If the example had gone evil and decided to give you a 4 input problem, then it'll be every 8. But okay, so that's all that is. So again, just doing my OR, just look at my values. Always, as long as some things are 1, we'll get a 1. And we need both of them to be a 1. So no, 1. An exclusive OR is where they're different, which is these 2 rows. Okay, but it's the context of the question that's going to matter, whether you use noughts and ones for your truth tables or whether you use truths and falses. Okay, right, so that's nice and simple. Right, let's have a look at how we might draw a custom truth table for a stupid circuit that I am now going to make up. That has no meaning in this circuit. So I'm going to have 3 inputs, but I'm going to use the logic gate symbols. I'm going to actually draw what looks like, well, if you can call what I draw as logic gates. Right, which symbol is that? And, correct. So it looks like a D from and. I don't know where that's going yet. What is that one? Not good. So that takes it. You can probably spot that on any circuit diagram because it's the only one that'll have one thing going in it. So it must be not. It's the only one that's got 1. And then the one that's impossible to draw without looking stupid. I can never draw this. What's that symbol? Oh. Yeah. Well done. You managed to guess the Picasso version of all there. Right. What I want to do is I want to try and draw a truth table to represent that circuit. So the first thing we always start with, how many inputs have we got? We've got 3 inputs. So when I draw this table, I need to say A, B, C. Now, when we're talking about binary, okay, if we use 3 bits, how many different combinations of noughts and ones are we going to get with 3 bits? What's the biggest number you can represent with 3 bits? Think of it. 7, yeah? So 7 is the maximum number. So how many different numbers can we represent though? 8. Excellent. Okay, so we're going to have 8 combinations of noughts and ones in this example. But in order to do this the easy way, what we can say is start at the right hand side, alternate every other line. So say, nought and a 1, nought and a 1, nought and a 1, nought and a 1. The B, we're going to alternate every 2. So we're going to say nought, nought, 1, 1, nought, nought, 1, 1. This one's going to alternate every 4. If they're in line, it'll be a miracle. Okay, so that's our 8 combinations. What we do it in that regimented way so that we don't miss any combinations out, because that would be a disaster if you repeated yourself. Okay, right. So now we can do the build-up of the table. So what we've got to do, I'm just going to draw these lines, very wobbly lines, to give us a chance. The pen's running out, even though it was a new pen 5 minutes ago. Quality pen. All they do is kick off a lot of smell. They don't seem to kick off much ink. Oh, that's gone right out of line now. Hang on. I should have drawn the lines first. One more. Right, so they're going to be my inputs. So all I need to do, even though it looks like, oh, scary, there's 3 gates on here, just take it 1 gate at a time. So we know that the inputs to this AND are A and B. So we've got A and B. What other symbols have we got for AND that we could use? Dot. Full stop, yeah. Because AND is sort of a multiplication, okay, if you do 0 times 1 you get 0, or 1 times 0 you get 0, but if you do 1 times 1 you get 1, so that's where that comes from. So you can say A dot B, okay. Bearing in mind that the exam board, I think they're going to use these symbols, but they have to accept these, because these are in common use. That's a problem. When you look at resources, okay, and things like that, and you're looking up stuff on the internet, you'll see loads of different symbol types. I think there's about 5 or 6 different types. Right, so all we've got to do for this one is you say, okay, A and B. Now we've got a load of repeats here, which we might have if ever could have carried on filling them back in. We've got a load of repeats, but we make sure we do the duplicates. So we got nothing there, nothing. No, they're not both there, so that's going to be no. That's going to be no. That's no. That's no. The last 2 are going to be 1s. Yep. Okay, so I'll just tick that one off. Right, the next one is not C. So let's do not C. What other symbols are there for not?
The one above the...
Yeah, the one above. That's that is the letter with the gun, as we like to think of it. Well, you can think of it like that. You don't have to think of it like that, but you can do that one as well. Okay, they're the 2 common ones. Right, so not C. Make sure we're looking at the right column, otherwise we'll make a total mess of this. So we're just going to invert C. Okay, so that's that one taken care of. Now, this next one hasn't got anything to do with A, B and C, but it has got something to do with the outputs of these 2 gates. It's an OR symbol, okay, so, and it's the OR of what? So what I'm going to do is I'm going to build it up. So I'm going to say it's that or that. So it's going to be, I'm going to put it in brackets just for clarity. So it's that or not C. That doesn't mean the C's approaching A and B with the guns in order to shoot the bullets at it, the dots. Right, what other symbols have we got for OR?
Plus.
Plus, yeah. Plus is the common one. Okay? We'll come on to that more in the second year when we're doing all the Boolean algebra stuff, when we'll see these. Right, again, so this time we're going to write what this representation is. So we're doing an OR, but it's an OR of these 2 columns. So we've got, wherever there's a 1, we get a 1. So we're going to go not 1, yes. Oh, nothing there. Yep, we've got something there. Oh, we've got nothing there. We've got something there, got nothing there, and then we've got something in the last 2. Okay, so what we've done without even thinking about it is we've actually written up the Boolean algebra for that circuit without even worrying about how to do that, just by building up that truth table in steps. Okay. I don't know exactly what context the exam board are going to mess about with this. We'll definitely get some in the second year, but it is potentially there for the first year stuff to be able to do this. Okay? Anyone got any questions about that? As long as you do it methodically and you don't cock the first bit up doing the inputs, they're pretty trivial to do because the actual logic gates are super simple. The fact that on a CPU someone sat down and did, well, not one, but a team of people have sat down and worked out how to connect 2 billion of these things together, that's the magic thing. Okay? But yeah. All right. Okay. I'll stop the stream on that one, unless it's already cocked up anyway. Oh, I might have paused it. No. I hope it's not dead. Okay. Right. Let me pause that. So what I'm gonna